Good morning students. Today we will be discussing about introduction to quantum mechanics and wave particle duality. So before going to quantum mechanics, we should understand the difference between classical mechanics and quantum mechanics. Okay, if we go for classical mechanics, for which type of objects classical mechanics is applied? So it is applied for the objects which we can see from our eyes. That is for macroscopic particles. For the objects which we can see, which are macroscopic, for that we can apply classical mechanics. Quantum mechanics. Quantum mechanics is applied for the particles which we cannot see from our eyes. This is for microscopic particles. For example, atoms, electrons, neutrons, protons, these we cannot see. For this, we need to apply quantum mechanics. Next, if we come for classical mechanics, here for the objects which we can see with our naked eyes, for that we apply Newton's laws. Newton's laws. Three laws. Newton's three laws are there. That Newton's laws we can apply for this classical mechanics. Next, in quantum mechanics, there are no Newton's laws. Newton's laws are not obeyed. For example, if I take electron will be revolving around the nucleus. It will be doing its work if you don't give any external energy also. So, here Newton's laws cannot be applied for microscopic particles. Next, classical mechanics. Classical mechanics is postulated by Newton. Newton has given classical ideas about classical mechanics. Next, Max Planck. Quantum mechanics is postulated by Max Planck. You might have studied about Planck's constant, H. If we find H, it is related to quantum mechanics. Next, in classical mechanics, energy is continuous. There are no energy states, there are no quantum numbers. Energy is continuous. Whereas in quantum mechanics, energy is discrete, means energy is emitted or absorbed in discrete packets which are called as quanta or photon. Means in quantum mechanics, energy is discrete, means it will be having discrete energy levels. We'll be having ground state, first excited state, second excited state, like that. We'll be having principal quantum number, azimuthal quantum number, spin quantum number, all these things, quantum numbers, we find in quantum mechanics. Whereas in classical mechanics, there is no quantum numbers, there are no discrete energy levels. Energy is continuous. Next, in classical mechanics, wave is a wave. Particle is a particle. Means wave behaves like a wave. Particle behaves like a particle. Whereas in quantum mechanics, waves and particles exhibits dual nature. Means wave behaves like a wave as well as particle. And particle behaves like a particle as well as wave. So this is the brief introduction about classical mechanics and quantum mechanics. So in quantum mechanics, energy is discrete. No Newton's laws. It can be applied for microscopic particles, and waves and particles exhibits dual nature. So these are the important things you need to remember for further topics. Next topic is wave particle duality. So before going to wave particle duality, we'll study about what is a wave. What is a wave? It is a spread out disturbance. It is some sort of disturbance. Next, you cannot give the location of the wave. We cannot find wave where wave is. Next, wave is specified by certain parameters. Means when I talk about wave, I refer only certain parameters, that is frequency, wavelength, amplitude, phase, wave velocity, intensity, time period, etc. These are the parameters I use for a wave to describe a wave. Particle. Particle means, for example, we are also a particles. So particle means particle is having certain mass and it is having definite position. Means I can give position of a particle. I can locate a particle. Next, particle is specified by, means When I am going to talk about particle, it is specified by mass, velocity, acceleration, momentum, energy, these terms. So wave is specified by other parameters, particle is specified by other parameters. So wave and particles are quite different. But we are saying that wave and particle exhibits dual nature. We'll see how it is possible. Okay, now first we want to prove radiation exhibit both particle and wave nature. Radiation means it is a wave. Radiation means it is a wave. So we want to prove wave exhibits both particle and wave nature. Okay, now first we'll prove wave exhibits particle nature. So first, what shall we prove? Wave exhibits wave exhibits particle nature. So according to Max Planck, energy is emitted or absorbed in discrete packets, which is called as quanta or photon. Here energy of photon is given by E is equal to h nu, where h is Planck's constant and nu is frequency. So energy, here wave is described in packets, discrete packets, which is called as quanta or photon. Means wave is described in terms of a particle. He has considered wave in terms of a particle. Next, Neil Bohr atomic model. This also says that the energy difference between two levels is again a photon. So here wave is described like a particle. So not only these, Einstein photoelectric effect, Planck's radiation formula, Neil Bohr atomic model, Compton effect, black body radiation, these all experiments suggest that radiation exhibits particle nature. That is, wave exhibits particle nature. So what are the theories? What are the theories which says that wave exhibits particle nature? One is Max Planck radiation formula, Einstein photoelectric effect, Neil Bohr atomic model, Compton effect. Next you can add black body radiation. So these suggest that wave exhibits particle nature. Next, in order to prove wave exhibits wave nature, which experiments proves that wave exhibits wave nature? For example, which experiments prove that light is a wave, light exhibits wave nature? You might have studied in the intermediate Young's double slit experiment. Young's double slit experiment, which is based on interference. So, interference and diffraction are the experiments which proves wave nature of a wave. Not only wave nature of a wave, these are the experiments which can prove wave nature for anything. So, wave nature of a wave can be proved by interference and diffraction experiments. So here, therefore, we can prove that radiation exhibits dual nature, both particle and wave nature. So radiation exhibiting wave nature is proved by interference and diffraction. Radiation exhibiting, wave exhibiting particle nature is proved by all these: Einstein's photoelectric effect, Planck's radiation formula, Neil Bohr atomic model, Compton effect, black body radiation, all these things. So, no single phenomenon exhibits both wave and particle nature simultaneously. Means in single experiment, I cannot prove both wave and particle nature at the same time. If I take photoelectric effect, I can prove particle nature of a wave. If I take interference experiment, I can prove wave nature of a wave. So, no single experiment is there which can prove both the natures. So this is about wave particle duality. So thank you very much.